Go ahead.
Do you mind if you burn your face?
Not at all. Burn my face. You know how to show a guy a good time. Hey everybody, Adam Savage here in my cave to talk about 3D printing technology. We here at Tested have been following this technology since its inception, and we have long looked forward to the day when it moves out of being simply a prototyping technology and becomes a real at-scale manufacturing technology. Well, turns out that's already happened. This is the adidas 4DFWD, a unique sneaker with a 3D printed midsole made by Carbon. We recently visited the headquarters of Carbon, where they explained to me how the Adidas engineers designed this lattice specifically for 3D printing and how the materials scientists at Carbon made that design a reality and they were able to produce it at scale. Ian, Ladon, tell me about what I'm holding on to here.
What you have here is what we call the 4DFWD midsole. It's been designed and developed to solve one of the fundamental problems of running, and that is that every time your foot hits the ground, it comes to an absolute dead stop. Then you have to re-accelerate it, and again.
And so this midsole has been engineered to provide more push off the stop?
It's been engineered at a fundamental lattice level so that every vertical impact is converted into a forward motion. You might be able to see in this little cube here with the material. So when you give that a squeeze,
it moves in a direction.
It moves in a direction rather than vertically down.
So what is that? And that, oh, right. So if it's pushing up that way?
Yeah. Exactly, yes.
Whoa. Okay. So this is the fact. Okay, wait a second. This is 3D printed to provide a directional spring. That's not something you can do in any other way.
Exactly.
Okay, talk to me about how this project starts. How do you begin? Who calls you and says, we want to do this?
So it started with our athlete science department. They had this fundamental insight that the impact and the contact, if we can make that so you could continue moving forward, it would result in a smoother run.
So that the shoe takes the energy it's given and adds a little more to the runner.
It just damps that impact, pushing you forward, smoothing that impact, reducing those braking, aggressive forces, and just, smoothing things out for you.
When this was first conceived, was 3D printing at all able to do what you needed?
Do you want to speak to that?
I would say that the 3D printing would, but the lattice structure, the fundamental structure that would provide that forward motion was not there. So we would be able to print any lattices, but we didn't have the unique lattice performance to give us that.
So how many iterations did it take to find that lattice?
Oh, it's a lot. So we had a big library of like 5 million different lattices that we could go and pick from, but all of them had this sort of isotropic behavior. You wouldn't get different performance. It was all compression, normal response.
So it behaved like a normal sponge.
Exactly.
Because it was monolithic or uniform.
Exactly.
All the way through.
Uniform all the way through. So we thought about how we generate these basic unit cells, and we thought about how can we break this symmetry. There were lots of iteration, lots of trial and error till we come up with this idea of breaking that fundamental lattice into different subcubes and then filling them with different lattices that has different compression properties.
And different directional compression.
Exactly.
properties.
And then that was breaking the whole symmetry in our system and was causing to create this one. So we come up with that fundamental and we test it and say, yeah, the fundamental works. Now, what's the best performer? That would gives us the durability that we wanted, give us the stiffness that we wanted to get, the lightweight structure that we want to get, the amount of the forward motion we were looking for. And that's lots of iteration again, trial into that mechanism to find the one that we call bow tie, because it looks like a bow tie.
Oh, it's called a bow tie, right? Because I see that little...
Exactly, it looks like a bow tie shape.
Oh, that is so cool. Okay, so, and this is your midsole in the sneaker.
Yes.
Yeah.
Now, I'm just curious. I'm assuming that most of this is mechanical engineering, but there's also some aesthetics going on.
Oh, yeah.
Yes, absolutely.
Talk to me about how that balance works.
Yeah, it's something we are the engineers, but we've worked very closely with our design team.
Yeah.
And one of the really interesting things we can do is we can have the functional parts inside the shoe, and then the outside surface can be more of a blank canvas from a design perspective.
So you get to do stuff out here that's just for the aesthetics.
Yeah.
You don't have to, and you're not compromising the mechanicals.
And we try to make the external aesthetic representative of the function. So
it is telling a story.
Yes.
Exactly.
This is telling a story that
Yes.
there's nothing else that, because I know there's nothing else that could do this right now.
Yes,
Yeah.
exactly.
So once Adidas comes up with the idea for a lattice, that's just the first step. Then they needed a partner to produce it. And I'm talking to Jason with a great job title, Senior Vice President of Materials. Is that right?
That's correct.
Here at Carbon, you helped Adidas get this across the line. Talk to me about that process.
We did. So one of the biggest problems we had to solve was around materials. So how do you make an elastomeric material that can print in these lattices at relevant speeds for production, but also have the mechanical properties required for meeting the really strict demands of a running shoe?
It's also a really, I mean, the bottom of a shoe is, I think, would be classifiable as a toxic environment.
That's right.
For a material. It gets a lot of weathering, there's a lot of chemical
Absolutely.
exposure.
UV light. We have hydrolysis that we have to worry about of the material. So it's basically water degrading the material over time.
Right.
So one of the things so we knew that there's a category of materials that will work for this, and that's called polyurethanes.
Mm-hmm.
And so polyurethanes are used in lots of different applications, but usually in the form of foam. And so we had to figure out a way, how can we make a polyurethane type of material that meets all these demands, but again, solves for this giant equation of print speed, color, and mechanical properties. So that was our task.
And the difference here with Carbon is most 3D printing companies are printing with materials they are obtaining, but you guys are literally manufacturing
Correct.
the chemistry of your materials from scratch.
That's right. Yeah, and so we do I have a team of about 40 people, and we do all of our formulation and innovation around materials in-house. We have partners that we work up for scale up when we go to really high volumes, but all of the R&D and innovation happens here in this lab.
So you get the idea for the lattice, you know that it's going to be within the framework of urethanes. What then do you do to find the right one?
So this is where we get into some polymer chemistry here.
Excellent.
And so typically 3D printing has sort of what we categorize as used single cure materials. And so these are materials that upon exposure to UV light, they solidify. And there's a range of what we call monomers that we can use. And
when you say single cure, you mean it as opposed to like you mix two parts together,
correct,
and they cure together.
Which I'm going to get to because that's what we ended up doing.
Oh, okay.
So single cure. So a typical 3D printing resin. Let me draw on the whiteboard here. So you might have these are sort of carbon-carbon double bonds, right? And so you might have these types of monomers floating around in your solution.
Yeah.
You have a free radical photoinitiator that sort of sparks off. This is called a radical, right?
Okay.
And then this kind of starts to zip this whole chain together. And
when
so
it's exposed to a certain kind of light.
Correct.
Okay.
So the light, this is sensitive to a certain UV wavelength of light. You hit that, forms a free radical, and then these kind of zip together into a chain.
Okay, so just to like translate that for people watching, if we think of these molecules as Legos and the light as like a 6-year-old child,
that's right,
that starts to connect those Legos together automatically.
Perfect analogy.
Okay, good.
That's right. So you can form linear chains, but usually what you do is you form what are called cross-link chains. Okay, so this is basically just like a big network of polymers, and so that's UV curable materials. That's how UV curable coatings work, and it's how a lot of 3D printing materials work. Okay, so this was kind of where we started. Mm-hmm. And what we found is that the materials that work in this general kind of workflow didn't have the properties. They didn't have the durability or the elasticity that we needed for the running shoe. But our printer is still based on UV light, right? So we have patterning of UV light in order to print these objects. Mm-hmm. So that was sort of a tricky problem. Okay, we have to use UV light, but the materials that typically work with that aren't going to get us there on their own. We had to figure out, how can we solve this problem? We have UV light, but we need better properties. So we started using what are called dual cure. So I can have my UV curable monomers here. And what we started doing, and think of a different set of Lego blocks now that are thermally curable. Let's just kind of represent, this like this, right? So we have these types of AB kind of systems here.
So you get one type of, when you apply a UV light, that initiates one kind of bond,
That's right.
and the heat initiates a different kind of bond.
Nailed it.
It gives you
Exactly.
an extra mechanical property?
Exactly. So when we
Wow.
just do UV, okay, so we hit UV, we form this same type of network, right?
And that yields like a kind of a rubber, like something that can move in multiple directions.
That's right. So this is something we call the green state. Well, we can do this for rubbery and rigid materials. Okay, so we first form this UV network.
Yeah.
Now I have all these thermally curable monomers are sort of trapped in there. Okay, so this all happens during printing.
Yeah.
So I'm patterning this. I'm curing my initial UV network, and I've trapped these sort of monomers in this kind of molecular network that's being formed.
Mm-hmm.
So that comes out of the printer, and now I have my midsole, it's dripping with resin.
Oh, wow, okay.
And then we clean that residual resin off. We're gonna show you that in a minute.
Yeah.
Then I take this and I go in, and like you said, now I add heat, and now I start to stitch all these together, okay, into a different network. So what you end up with, so we have our UV network, and then now I've made these long polyurethane chains. So these can be polyurethane precursors or polyurethane monomers. Now I have a mix of this initial UV network, but I've made what I wanted, which is long polyurethane chains. And so that's how we're able to achieve these mechanical properties.
I want to pause for a second to zoom out.
Sure.
Because this is, you live, eat, sleep, and breathe this technology right now. But it's also really true that you are right now like carbon, and you are surfing on this wave way out at the forefront of this technology. So despite all this R&D that you've done so far, it must be really exciting every now and then when you realize you're still at the very nascent part of this.
Yeah, so this has opened up an entirely new area of chemistry. So instead of being confined to the box of materials that work here, we now have a much bigger playground that my team can play around with and formulate new materials.
And I'm assuming that you could also attenuate how many bonds you create by the amount of heat and the duration of the heat. Is that also
absolutely.
true?
Yes. So baking schedule is important. So there's a lot more. The other thing is there's a lot more thermally curable materials out there than there are UV curable materials. You're kind of limited in chemistry. So again, we have this much bigger, world of chemistry to play with.
But you still require the UV curable to create the situation for the thermally curable.
That's correct.
Oh, that is really cool.
That's correct. That's
correct. So the first time I visited here, I got the spiel about how you guys were a chemistry company.
Yeah.
Right?
Yeah.
This is so exciting to see this elaboration, multiple processes yielding these multiple modalities inside the material.
Yeah. It's been really fun, and I think we're just getting started.
So how long after Adidas calls you and you start working this out, what is the process by which you're testing each of these? Are you putting them on people's shoes and having them run through the desert?
Yeah, not initially.
Okay.
but that is kind of the final test. Is someone actually, Adidas has people who run in the shoes for hundreds of kilometers in this kind of ultimate durability test, and you have to pass that.
But
before you get to that, so we use these types of instruments that you can see around here.
These are the stressors.
These are some of them. Yeah. So this is what we call dynamic mechanical analysis. So this is evaluates the mechanical characteristics of a material over a temperature range.
And it stresses it and applies force and then monitors how it changes over time?
Correct.
What is this? This is...
So this is a bust of your head, I believe, that is made of the material for the Adidas 4D Forward shoe, which is called EPU 44. And so you can feel the squishiness of it.
Oh, dude. So this... I feel weirdly seen.
So another really cool thing about this material is these kind of basic units that used to make up the polyurethane. About 40% of that material is what we call bio-derived. And so that means it started out as corn.
Ooh.
And so we can, basically this is from our chemical suppliers. So this is a product called Cistera by a company called DuPont, Tate & Lyle. And they grow corn, use CO2 and sunlight to make the plant. And then the plant generates sugar, and then you can convert sugar into polyurethane precursors.
No way.
And so 40% of that material is derived from plants. And that has a really important impact on carbon footprint, because rather than using petroleum-derived sources to make your raw materials, you're using plants. And so that's just an added benefit. And we didn't have to sacrifice performance. In fact, we got better performance from the plant-derived material.
Amazing. That's amazing. Carbon footprint. I see what you did there.
That's right.
Okay, I'm going to pause right here and just talk about a really cool aspect of how they clean these prints. When they come out of the machine, they are still wet with resin. And in my 3D printer, I have to wash that resin off with isopropyl alcohol. And there are industrial solvents for doing that, but they are industrial solvents. That is hazardous waste. Here at Carbon, they spin the print and spin the resin off, and then, come on over here, they recapture it in buckets and are able to reuse it. This is tens and tens of thousands of pounds of industrial waste that doesn't get produced every year because of that. I really appreciate that. All right, guys, so this is fresh out of the machine, and then it was spun clean. How long did that take to make that piece?
So it spends less than 30 minutes in the printer. And then we take it out of the printer and we put it in one of those spinners over there. The spinner spins over about 3 minutes to just rip all that excess gooey resin off there so it's mostly clean. And then it's ready to go into the oven.
I would imagine, that's incredibly short to me.
Yeah.
I would imagine that 30 minutes was a hard fought you worked really hard to make that as short as you could.
Yes.
Absolutely.
The first ones of these that we did were hours.
Yeah.
So the very first prints were hours, and then methodically just beat that down over time for the last few years to get it down to this under 30-minute target that we have.
And that's both a mechanical problem, a software problem, a material. It's all of the problems.
All
at
of the
once.
above. Absolutely. Yep.
And am I correct that you probably still think of this as too long? I mean, I know that you're manufacturing, but you want to reduce that.
There's always pressure to make it faster, for sure, because your print speed directly dictates ultimately the cost of the part, because it dictates your throughut.
Right.
So all of that.
How many printers can produce X per day?
Yeah, that's right.
And then we get excited when we overload the equipment downstream of the printers where, okay, the spinner can't handle it anymore. Now they need to get another spinner because the printers are too fast. So there's all that balance stuff too, which gets really interesting when you're in the factory environment that, that speed matters, and you get a nice balanced factory. Like turning up the speed means downstream effects that can get pretty interesting.
So at the very beginning, when you're starting this dance with Adidas, figuring out what the art of the possible is, there must have been a moment where they said, we'd love to make X per X. And you just felt like, holy cow, I don't know how we could get there. Yeah.
I presented that slide to Adidas leadership back in the day. And yeah, I mean, the numbers that were on the slide were like, we've never demonstrated anything close to this, but we can imagine maybe we could get there with a lot of innovation and a lot of work, and we're pretty close to what we were saying we would get to, which is, it's super exciting, and it's been really exciting to ride that innovation and that development over the last few years.
I have to say, that strikes me as unique for a company as big as Adidas to be willing to kind of let a target remain soft while you figured out what was possible.
Well, they're a pretty unusual company, and there's one of the things that we noticed when we met with them is this is a company that understands innovation, that they understand what a technology looks like in the earliest stages, and they're willing to get in and bring it up the mountain with you and really work through all the challenges and be patient, because on the other side of that, they're going to have this amazing new technology, this new cushioning technology that lets them make better products.
So we're standing in a room here where you guys work out the actual manufacturing of the parts.
Yeah.
It surprises me how small this room is. And yet I hear that you've turned tens of thousands of parts out of it already.
Yeah,
that's right.
So what is the next stage? After this has been spun, what is the next thing that happens to it?
So there's an interesting detail about this. So you'll notice that this is on a curved tray.
Yeah.
So one of the innovations that let us increase that speed is we actually print these things flat. Right?
Oh, so you don't print it with its final shape.
Right.
That's right.
Because it's easier to print flat.
Exactly. And if it's easier to print flat, it's faster, and it uses less resin. And then you put the shape into this thing that goes into the oven. And when it's in the oven, it's going to take the shape of whatever it's sitting on. And originally we struggled with that because we're like, okay, we need to make these molds. What a pain in the butt this is. We don't want to deal with it. We don't have to hold it into the shape. And then we had this realization, oh, wait, we can make a feature out of that.
Right.
Whatever we put it on is going to
That's
take that shape and it's going to really increase the throughput. So it was a really important
And
innovation
that
for us.
ties back to the chemistry. So like we talked about, when you're in that green state, so this has just the UV portion of the chemistry activated
It
right now.
does not yet have the
The
heat.
thermally
Got
curable
it.
stuff is still trapped in there. And so when you reshape it and activate that thermal chemistry, you're now locking in that final shape. And so it's sort of this nice benefit that allowed us to bypass a lot of challenging things.
You could end up with polymers attenuated to cure at different heating rates, and you could put it in different shapes in multiple heating
That's
processes
right.
and get multiple
That's
properties.
right. That's right.
Oh, this is thrilling.
Jason has a job for you.
I mean, as soon as I saw this on this and I realized that this was your cookie tray
Yeah.
for the piece, and this is exactly the same size that they're using in China as they're producing this,
Yep,
yeah?
exactly.
Yep,
There's
that's right.
there's thousands of these. They can change the position of this back piece to set what the angle of it says. For a longer shoe, this needs to be a little bit farther back.
Oh, because there's a little kick on the heel.
There's a little heel.
Okay.
They call it the heel kick, exactly. So they adjust this for the size of shoe that they're making, and then it goes into the goes over into the ovens on the other side of the room.
So this is a production piece, right?
Yeah.
Correct.
And that's really interesting from a manufacturing standpoint. You don't need a giant injection molding factory to turn out the same part that they're turning out in China.
Exactly.
Correct.
That's an incredible advantage, isn't it?
Anywhere where one of these printers is, you can make one of these things.
That sort of shortens your distance from idea to product in a significant way.
And it allows for multiple iterations to happen very quickly, so that you can go out into your testing and you can go through hundreds of designs before you lock in on the one you like. It's very difficult if you're using molding and these types of other technologies.
I had not considered that one of 3D printing's disadvantages, i.e. that each printer can print one thing at a time, yet could be an advantage because you have the same manufacturing facilities that the
that's right.
factory does.
And one of the really interesting things about it is how well it fosters collaboration. Because this facility is a kind of upstream development facility where we work with Adidas to tune the geometry, to tune printability, things like that. So our engineers here will tune the print scripts, tune the printing to make it print really well.
Right.
And then we're like, okay, so we can do that on 5 printers here. Let's get it into the big factory. So they'll send it out in the evening, and that when China's waking up, and then it'll go into production in that factory.
And all their shoes start coming out faster.
Minutes later, and it'll start coming out faster, and we'll be able to get that data
Oh,
really
and because
rapidly.
you're watching the machines
Yes.
live online the whole time.
Yeah,
That's right.
and then it goes through their QC process. Each one of these has a data matrix code on
That's
it
wonderful.
that tracks where it was printed, how it was printed, all the parameters.
So anything goes wrong with QC, you know precisely which machine it happened on.
Exactly.
And go look at
and
it.
for speeding this thing up, we work on the algorithms to really optimize every step that it takes, every pixel that it turns on, all that, right? So by tracing that back through this data, we can say exactly what script it was used, exactly what calibration parameters were on the printer, all of that stuff we know and understand, and we can use that to feed back into the system and keep optimizing the performance, both from printing from kind of a factory optimization point of view, as well as making the product as good as it possibly can be.
What's really fascinating to me about carbon is most companies do a thing and they know how to do it, but you guys are like 4 different companies at once, and all these parts really affect each other. So the chemistry affects the manufacturing, affects the design, affects the engineering.
Absolutely.
And then to keep all that sort of bubbling along at the innovation level you guys play at requires so much sort of, I feel like it's a very plastic mind this company has.
Yeah, it does. And it absolutely requires collaboration across disciplines, so that we aren't just sitting back saying, well, I did my job, that's your problem. No, we have to figure out how to get the part to print out, because that's what matters.
That is really, really neat. Guys, thank you so much. This is, we've been talking about this shoot for a while. I've been immersed in what you guys have been doing, and yet still I feel like I had no idea how deep the rabbit hole goes. It's been thrilling. Thank you.
Absolutely.
I really appreciate the storytelling here, because it's super compelling, and a lot of the folks around here are wearing your shoes. It's really awesome. I'm curious if you must be percolating all sorts of ideas for the future.
Yeah, so I'd say running, we're talking about directionality of properties.
Yeah.
Running's our simplest case, because you go in one direction and it's forward. But we don't have to orientate this directionality in one direction. We can split it to the side. We can put it at different angles. So then you think tennis, you think basketball, where you're moving sideways more often. You can apply it to this as well. So really, we're just building a toolbox, and then we can pick the best tools, the best lattices to deliver the function that we need for the different sports.
This is really exciting. I mean, there's very little difference between getting it wrong and being too far ahead of the curve, but it really feels like you guys hit this sweet spot of, you know, I didn't, when I first heard about this, I thought that that's crazy, the idea that 3D printing could scale for international manufacturing. And yet you nailed it. It's really amazing. So what is next? Are you guys going to make sleeping pods for astronauts?
Maybe not sleeping pads for astronauts, but you know, what this allows us to do is really explore different fundamental properties that we couldn't, and find the applications that fit.
Right.
So I know you're very interested in impact protection for your spacesuit.
Yeah, absolutely.
Instead of developing a lattice that returns energy and returns it forwards, we could look at something that damps that contact. We'd also have the unlock. We have to have this go through 500, 600 miles of running. That's a lot of 100,000 impacts to survive.
Wow.
Something for a spacesuit might just be, you know, once, and it survives that fundamental impact.
Guys, it is really, really thrilling to see a brand new manufacturing process successfully being used. It's amazing. Thank you.
Thank you.
So this is the flame retardant material.
Okay.
So if you try and burn it,
You know how to show a guy a good time.
Wow, it gets like evil looking.
like you can keep trying to burn it.
Yeah, keep going.
Catch fire.
Yes, yes.
But see how it just immediately self-extinguishes?
It won't continue burning.
And so you
won't
think
burn,
about things
yeah.
like servers and automotive components, aerospace components, is where you want that flame retardancy, that self-extinguishing type of property.
Wow.
Yep.
That is not common. That's really neat.
Yeah.